Thank you very much. I'd like to begin by thanking the organizer for inviting me. I will talk about, my talk is going to be based on 3 papers, one of which has appeared end of last year. The other 2 will appear soon. So it is sometimes one hears people say that we know a lot about two-dimensional conformal field theories. I must say that I do not share that feeling because I feel like I know almost nothing about two-dimensional theories. Here's why. So I'd like to pose the following question. Consider two-dimensional unitary compact CFTs. By compact, I mean discrete spectrum and SL2R invariant vacuum, finite OP coefficients, and all that. With central charge C greater than 1, with no extra symmetries beyond Virasoro, that is, no conserved current primaries of any spin. One would think that such theories are ubiquitous, in particular for the purpose of investigating 3D quantum gravity in ADS3. One would think that generic holographic theories should be of this type. Now, can you give me an example? Well, first of all, rational CFTs are out of the window because they always have extended chiral algebra and therefore extra higher spin conserved currents. Free orbitals also have conserved currents higher spin. That wouldn't work. You might try to consider some theories with exactly marginal deformations. Well, in supersymmetric theories, you always have extended chiral algebra, even if you gauge it with R currents, say in the known 2,2 models, which can be made irrational. And if you give up on supersymmetry, nonlinear sigma model on Calabi-Yau spaces, I'm not sure if they really define fixed points. So I ran out of trick in my bag, and that means that there's a huge gap in our knowledge of, at least in my knowledge, of two-dimensional conformal field theories. Either we're somehow missing important constraints because there seems to be, I don't even know, an example of a theory with 0 twist gap in the spectrum of primaries, or we have been just completely ignorant about the vast majority of 2D conformal field theories. I think probably the latter is the case. We're just being very ignorant. So it seems that the only viable approach now, given that all the previously known technology has not been able to produce or does not allow us to access such theories, conformal bootstrap will be a suitable and only technique. Now, in 2 dimensions, one can make use of the crossing invariance for 4-point function on the sphere and modular invariance. And it is known by well-known arguments that combining modular invariance towards 1-point function and the sphere crossing for sphere 4-point function for all primary operators, that should be the complete set of consistent relations that define a 2D CFT. And on top of that, of course, I'm going to demand unitarity and compactness. For now, while it's hard to combine these ingredients together, for now I'm just going to discuss some results obtained by considering the modular invariance of just the partition function and from the crossing of the 4-point function. And I will always assume that my theories are unitary. So the modular bootstrap is simply, here I'm just going to discuss constraints from a modular invariant partition function and unitarity. Now, you might have thought that the constraints from the modular invariance of partition function must have been beaten to death by now. Surprisingly, that is not the case. So I'm not going to talk about rational theories, as stated. So I'm going to consider, I'm going to follow this approach of the modern reboot of the modular bootstrap, started with Simeon Hellerman. So the idea is very simple. I'm going to consider a partition function which can be decomposed into Virasoro characters. As I stated, I'm assuming that there are no conserved currents primaries of any spin. So apart from the vacuum character, all these other Virasoro characters are non-degenerate. And I'm going to obviously impose the condition that the coefficients are positive integers. And ask what constraint does this put on the spectrum and the degeneracy of the primaries. OK, this is what I said. The spin obviously has to be integer, so we just need to look at S transform. OK, so the approach is going to be well, this is really the same thing as the conformal bootstrap with the conformal block here replaced by the character of Virasoro algebra, which is much simpler. And so if you consider, we're going to be seeking some linear functional that acts on functions of tau and tau bar, acting on this modular crossing equation. So this functional d, if you act on the character, it produces these numbers, e, which depends, we call e, which depends on the conformal weights of the primaries. And I'm going to be seeking to have a useful constraint. I'm going to be seeking linear functional that has the property that when it acts on this modular crossing equation, act on the characters, it takes the same sign for the vacuum as for very high conformal weight primaries. So that this equation cannot be possibly satisfied. The equation that says this thing is equal to 0 cannot possibly be satisfied for positive coefficient d unless there exists some low dimensional operator primaries such that d acting on that character gives you a negative sign. OK, that's what I said. It turns out that a lot of constraints can be obtained in this way. Now, previously, in the work of Siemens Hillerman and follow-up work by Friedan and Keller, they considered certain type of linear functionals. We're going to investigate this more systematically using the same numerical methods that's been successfully applied to conformal bootstrap in higher dimensions. And we'll find much richer and stronger constraints. So here, numerically, we use the package designed by David Simmons-Duffin. And we'll be exploring, in principle, a complete set of linear functionals acting on this modular crossing equation. But in practice, we'll need to take derivatives with respect to tau and tau bar, but truncated up to some integer order, capital N. And we'd like to take n to be large to optimize such bounds. Here, I present a result from an upcoming paper. This red curve here, which almost look straight except for this kink here, it's actually not straight, it's a curve, is the optimal bound we obtain on, it's the upper bound on the gap in the dimension of primaries, regardless of spin, for such theories of given central charge. So here I apply central charge from actually 1 to 40. I'm demanding central charge to be greater than 1. Now, I'll just point out a few features. One can show analytically that the twist gap can be no bigger than c minus 1 over 12. That's this black line here. So the dimension gap is strictly weaker. The bound is strictly weaker than the twist gap bound, obviously, by definition. For c between 1 and 4, it turns out this bound is exactly given by c over 6 plus 1/3. This, by the way, is actually a new result already. Previously, in the work of Hillerman and Friedan and Keller, they concluded that at large c, asymptotically, the bound will be, while the dimension gap is bounded by c over 6 plus order 1 number. That will be something that's parallel to this orange dotted line here. But we found something stronger. This blue line has slope 1/8, but we found something that's stronger than that. So the asymptotic slope seems to be below 1/8 and actually below 1/9. Let me describe the asymptotic slope. Oh, sorry, actually. Here, there's a kink at c equals 4 where the gap equals to 1. This has an explanation. So if you're sitting on the boundary of the allowed domain by this analysis, it is possible that even though I assumed from the beginning that there are no conserved currents, primaries, it's possible to take a limit where the dimension of the left or right weight of the primary goes to 0, so it becomes conserved. But the character that enters my partition function is still non-degenerate. So at the boundary of these allowed domain, it is possible to have some partition function that corresponds to a theory with conserved current primaries. But there's also going to be a twist 1 primary of spin less than 1, of spin 1 less, so that the decomposition of the partition function into non-degenerate characters still have positive coefficients. So for that reason, there could actually be theories with conserved currents sitting at the boundary here. And actually, the kink at c equals 4 and gap equal to 1 is realized by the theory of age-free fermions with the GSO projection. So that you can verify that has the right property. But ultimately, that's not the kind of theory I'm looking for, but nonetheless, it sits at the boundary, it sits at this kink here. If you plot, this is the plot of the ratio of that gap divided by central charge. And maybe it's hard to read here. These are the bounds obtained by going to higher and higher order in the truncation on the derivative order in the linear functional. So ultimately, we would like to optimize this bound by taking all derivative order linear functional. And there's the fitting, which is the black curve here. And you see the asymptotic slope of that bound in the central charge drops below 1/9, in fact. Now, the numerics become more difficult at a larger central charge. Here's roughly why. If you go back and look at this linear functional, we can actually optimize this. We can find one unique optimized linear functional that gives the strongest bound. And if you replace this partial z, which is like log of tau, by a parameter, you can plot what that function is. That's going to be some degree n polynomial. You can see what the polynomial looks like at larger values of n. For c equals 10, it looks like this. It looks like it can be perhaps well approximated by some low degree polynomial. But for e equals 100, it becomes something like this. And as you can see, the polynomial approximation will be inefficient, suggesting that perhaps the optimal functional should be of some form of an integral transform rather than taking derivatives. I'll just leave it as that. I mean, inspired by this, one might try to guess a optimal linear functional to begin with and try to prove there's such a bound at large central charge region analytically. We haven't been smart enough to do that, but maybe you'll be able to figure out how to do that. One can investigate the gap in the same philosophy, investigate an upper bound on the gap of just the scalar primaries without putting any assumption on non-zero spin primaries. Then the previous bound I plotted was this black line here. The bound on just the scalar primary, which will be strictly weaker, is this red curve here. It has more features. For instance, at this point, c equals 8, the gap is actually exactly equal to 2. There's a bound on the gap. So in particular, this implies that for this generic type CFT I'm talking about here, if the central charge is less than 8, there has to be a relevant deformation. That is a new result. You can ask, is there something that saturates this bound at the kink? There is. It's actually the theory of 8 compact bosons at the holomorphic factorization point, described by the Narain lattice associated with the root lattice of E8. Now, this plot looks nice. I'm just going to extend. But surprisingly, the bound blows up at c equals 25. This shows how this bound on the gap actually blows up near c equals 25. And numerically, it's kind of hard to get it, but we can do a fit of where it blows up and thus reach c equals 25. We don't understand why that's the case, but there's probably a simple explanation. In other words, from modular invariance, it seems that for c greater than 25, there seems to be no restriction that will tell you that it has to be a scalar primary. It's a bit strange, but that's what comes out of this analysis. You can bound the degeneracy as well. So for example, if you look at c equals 1, of course, all known c equals 1 theories have higher spin conserved current primaries. But as I said, for the reason I said before, they can fake this kind of Pareto function I want and will still survive the analysis, survive this exclusion criteria. But you do actually see all the various interesting theories. So if you this comes from the numerics, you can try to put the upper bound on the degeneracy at the gap. And then you discover special values of the gap where the bound can be, say, 4 or 2. This corresponds to the compact boson at special radius, at special radii, and all of that just fall out of these numerics. Of course, if you explicitly, one can also, let me just show another plot. This is for c equals 4. You can also find this degeneracy bound, the upper bound on the degeneracy at the gap, which blows up when the gap drops down to c minus 1 over 12, which is the Liouville threshold. Anyway, now, if you assume a gap in the CFT, which is below this maximal gap, below this upper bound, but above the Liouville threshold, then there is an actual upper bound on the degeneracy at the gap, which we can determine numerically. When you do so, that bound, degeneracy bound will be obtained by a specific linear functional of the type I described earlier. If you take that linear functional and act on the characters, you'll find some zeros. These zeros will correspond to the actual spectrum of the higher level primaries. We call these the extremal spectrum, which is the spectrum that maximizes the degeneracy at the gap. And we produce all the known theories in this way, just numerically. They just fall out of these, the zero. This is a log plot of the zeroth of the optimal functional acting on these characters. OK, some other examples. OK, now I will switch gear and talk about the constraints from the crossing invariance of the sphere 4-point function. Now, this program obviously has been very successful in both 2 and higher dimensions. Now, I'm going to revisit this 2D problem using these semi-definite programming methods. And typically, we'll consider the crossing for some simple external primaries. It could be some low-dimensional operator, marginal operator in the theories with marginal deformations, or some BPS operator in supersymmetric theories. And we'd like to, in this way, we'll be able to constrain the content of the OPE from unitarity and crossing. So quickly describe some of the results in 4,4 and 2,2 theories, such as K3, which include these K3 CFTs, supersymmetric nonlinear sigma model on K3, or Calabi-Yau models, and other more general models. Our goal here is to understand some constraints on the spectrum of non-BPS operators in the theory, and in particular, non-BPS operators that appear in the OPE of a pair of BPS ones. So if there's a conformal manifold, we'd like to understand the moduli dependence of the spectrum. With the 4,4, we'll be looking at theories with small n equals 4 superconformal algebra, focusing on the C equals 6 case for technical simplicity. We'll consider pair of marginal BPS primaries, say for the K3 CFT, and we'll study the superconformal block decomposition of the BPS 4-point function. There are 2 key ingredients. One is an efficient way to calculate, that allows us to calculate these blocks. It turns out these BPS blocks can be rewritten in terms of Virasoro blocks with shifted weights. This one represents weight 1. I won't have time to describe the explanation of this, but once you understand this conjecture, once you make this conjecture, you can check based on some physical reasoning by studying n equals 2 cosine models. You can check with this with a computer, and it's true. The second ingredient is so I said I want to study the crossing for the 4-point function. It turns out that a certain integral of the 4-point function, the cross ratio, can be calculated exactly as a function of moduli that is determined by a string, by space-time arguments. Essentially, there's a moduli space of the K3 CFT, and we consider a certain integral of the BPS 4-point function. It can be determined exactly by the data of the moduli space, which is parameterized by the embedding of a certain lattice. And that is obtained by studying higher derivative terms in the 6D effective action by compactifying type 2B string theory on K3. That's a long story I won't be able to go through, but I'll use borrow this result. So we feed that into the Bootstrap machine, and out comes the result. So here's one result. This is the bound, upper bound on the gap of non-BPS operators in the OP of a pair of marginal BPS operators for the K3 CFT. The horizontal axis is this integral of the 4-point function, which depends on the moduli in the in principle known way. In particular, in the limit where the K3 develops a A1 singularity with the BPS operator being the one associated with the resolving the modulus that resolves the shrinking cycle. This bound asymptotes to 1/4, as shown here by some numerical fitting, by going to a higher and higher derivative order in the linear functional. And that 1/4 is exactly saturated by the A1 equals to cigar theory, which is expected to be describing the modes near the A1 singularity. I'm just going to give you a little taste of the result for n equals 2 superconformal bootstrap. So here, again, we'll study OP of BPS operators, say a chiral one and an anti-chiral one. Now, we want to feed in the information of the chiral ring coefficient, which sometimes can be calculated exactly on the moduli space. in such theories. And then we want to constrain, let's say, the gap in the OPE of a chiral primary with anti-chiral primary. By chiral primary, I mean chiral primary on both left and right. OK, so a warm-up example is I take theory with equal 3 and R charge 1/3 for the chiral primary. This will be realized, say, by the twist fields of the supersymmetric T2 mod Z3 orbifold. The bound looks like this. So focus on this blue curve here. This lambda horizontal axis is the chiral ring coefficient. And the vertical axis is a upper bound on the gap of non-BPS operators in the chiral anti-chiral channel OPE. So you could ask whether this nice curve with these features can be saturated by known theories. And actually, the entire bound is saturated by nothing but the T2 mod Z3 CFT. Here's the moduli space of T2 mod Z3 CFT, the radius and B field. And in these places on the moduli space, they precisely saturate these parts of the curve. In particular, the saturated bound over here, you have to turn on some non-trivial B field. Now, you can consider a case C equals 9 and R charge 1, which can be applied to Calabi-Yau models. So one of the plots look like this. So again, this horizontal axis is the chiral ring coefficient lambda. In the case of a one-parameter Calabi-Yau model, that can be calculated using spatial geometry of the moduli space. The vertical axis, again, I'm plotting the gap in the non-BPS spectrum in chiral, anti-chiral OPE. It looks like this. In fact, there's OK, this is what I said. In fact, there's a kink here. And that is nothing but the large volume limit, which come from the computing free correlators. And if you do take another example, say the Z manifold T6 mod Z3 with the vanishing B field, let's say, you'll find that in the OP of twist fields, it populates this region, which is consistent with the bound. If you turn on B field, you get more. It populates more region on the bound. This is a kind of random sampling of Z manifold at different points on the moduli space. If you now turn on if you assume a gap in the chiral OPE above the first BPS operator, then you obtain stronger bounds of various features. And you can produce such a three-dimensional plot, which is here you have the chiral ring coefficient, the gap in the two channels, the chiral anti-chiral channel and the chiral channel. These are the gaps for bounds the first non-BPS operator in a way that depends on where you are in the moduli space. Some parts of these are saturated, in fact, by free correlators, free OPEs, but the rest remains to be understood. Let me just give you one last plot. This is assuming for various values on your charge, assuming you have a 2,2 super conformal symmetry with a marginal and thereby exactly marginal in this case operator, R charge 1, consider its OP with the OP of that operator with its conjugate, and assuming 0 chiral ring coefficient. Now, in the case of C less than 6, the chiral ring coefficient is forced to be 0 by representation theory. You get a bound of this type. And you can ask whether this bound can be saturated. Surprisingly and interestingly, you can take product of n equals 2 minimal models that happen to have a marginal super conformal primary. They sit right over here. And this part of the bound appears to be actually linear, but then you have some curve over there. And these are some of the results I would like to report. And I'll just conclude by saying that much of the full story is yet to be revealed, and the journey continues. Thank you.
In the first part of your talk, where you're discussing the modular bootstrap, so in the low central charge region, I know one theory which has been discussed in the literature by the center in particular, which is obtained by coupling 3 state Potts models. So that should feature very prominently in your plots. It has central charge around 2 and it has S3 times S3 global symmetry.
I think I know what you're talking about. I think that theory sits at a special point in the modular space of just the T2 CFT, which is a Z3 symmetric point in both the Kähler and complex modular space. Sorry?
I don't think it's exactly solvable.
Wait. You said you take the product of 3 Newton models. That's what you said?
You couple them by the epsilon I, epsilon J, and then it flows. So
oh, it flows.
Yeah, it flows.
Okay, but so what's known about the float theory?
Well, it's known experimentally that it exists, and it has but it would be nice to say something about it using your method. That would be really nice.
Okay, I would love to learn more about that. Thank you.
How much can optimistic can one be about bounding the large numbers of Calavia threefold using these methods?
So that problem has been investigated by Kähler and Guri, but we think we might be able to improve their bounds using a more systematic numerical analysis. It's something on our to-do list. We don't have the results yet. Shiraz.
In the first part of your talk, did you put the constraint that the coefficient of the characters of integers?
A priori, no, because it's hard to put in directly, but once you derive the bounds, you can go and check whether that is allowed. So sometimes you find that if you try to maximize, so one thing you can do is if the bound is saturated, is exactly saturated, then the degeneracy at the gap is actually fixed. So you can ask whether that's an integer or not. And generally, it may not be integer. Sometimes happen to be integer. If it's not, it means the actual constraint is slightly stronger. Numerically, this usually makes very little difference because these degeneracy bounds are generally pretty big. Even for C equals 4 or 5, it's for 100 or so, typically. But you do get stronger bounds by demanding that they are integers. But of course, if you don't assume the actual gap is exactly saturates the bound, then you have some room to play with. We don't have a very efficient way to take account of the constraint that these degeneracies are integer. That's something that's obviously important to understand. But there are many other constraints that we have not taken into account, such as consistent with OP and all that. It would be nice to combine those together, say looking at genus two-parting functions, something like that.
Any further questions? If not, let's thank Xie again.